You'd expect trapped to mean something is holding us in. It's worse than that. Nothing is holding us in. We simply haven't finished leaving. According to plenty of headlines, humanity left the solar system back in 2012. According to the numbers, we haven't gone anywhere. Voyager 1 has been racing outward for nearly 50 years, breaking its own distance record every single day. If it went dark this instant, every system failing at once, it would still die inside our own solar system. Not near the edge, inside. That 2012 headline came from something real. Voyager punching through the sun's magnetic bubble. But that bubble was never the true border. The real boundary is a region so vast, Voyager won't finish crossing it for another 30,000 years. Before another star ever matters, something much closer is standing in the way. Can we even leave? Most people picture the solar system ending at Neptune, or maybe Pluto. A tidy little edge, a clean line on a diagram. Follow the sun's actual reach, and that line disappears. Past Neptune, past the icy debris of the Kuiper Belt, the emptiness keeps going. Then, around 300 billion kilometers out, something begins. The Oort cloud, a shell of trillions of frozen fragments left over from the birth of the solar system, wrapped around everything we know. It isn't thin. It stretches for nearly 2 more light years past its inner edge, almost 15 trillion kilometers. This is the actual border, not Pluto, not the bubble Voyager crossed in 2012. And Voyager is still roughly 300 years from even touching it. So the question isn't, how far is the edge? It's what happens once we finally reach it. Picture threading a needle 1 billion miles wide, blindfolded, and never touching the sides. That's roughly what happened in January 2019, when a spacecraft called New Horizons reached a small, icy world far out in the Kuiper Belt, named Arakoth, more than 6.4 billion kilometers. You'd expect a belt scattered with hundreds of thousands of icy bodies wider than 100 kilometers, plus untold millions of smaller fragments to look like a minefield. Get close, and it doesn't. New Horizons cross the entire region without a single near miss, without ever needing to dodge anything. Not because engineers threaded a perfect path around danger, because there was nothing close enough to hit. Spread that many objects across a region that wide, and the actual gap between any two of them stretches for millions of miles. The Kuiper Belt isn't a wall of rock waiting to shred a hull. It's closer to a handful of grains of sand scattered across an entire country. So collision was never the danger. That assumption alone has quietly stopped a lot of people from asking the harder question. If nothing is physically blocking the way, why haven't we made it through? The Oort cloud waiting beyond it is even emptier. Its trillions of icy fragments spread across a volume so vast that neighboring objects sit millions of miles apart on average. Nothing is in the way out there, and somehow that's exactly the problem. Say Voyager somehow survives those 3 centuries. Dead by then, no power, no signal, just drifting. It still isn't out. Now it has to cross the cloud itself, and that crossing alone is estimated to take around 30,000 years. Add the 2 numbers together. Roughly 30,300 years after launch, in the year 32,000 or so, a silent, powerless machine finally clears the last of the sun's grip. For context, the oldest cave paintings on Earth are about 30,000 to 40,000 years old. We are asking a spacecraft to outlast the entire history of human art, tool use, and civilization, just to step outside our own front gate. That's the best-case scenario. Our fastest object. A straight line. Nothing in the way. If that's the best case, the next question writes itself. What if we just build something faster? Picture the launch pad. A rocket sits fueled and ready, engineers targeting a speed twice what we've ever achieved. To get there, the fuel tank doesn't just grow a little. It grows so much the rocket has to be built bigger to hold it. But a bigger rocket weighs more. More weight needs more fuel to lift it. More fuel adds more weight again. Watch that cycle happen 3 or 4 times, and the numbers stop looking like engineering and start looking like a trap closing on itself. To meaningfully double a spacecraft's final speed with today's chemical engines, the fuel required doesn't double. It can multiply many times over, sometimes outweighing the entire rest of the ship combined. Look at the numbers behind the most powerful rocket humans have ever launched. The Saturn V that sent astronauts to the moon weighed about 2.8 million kilograms, fully fueled on the pad. Strip away the fuel, and the actual spacecraft riding on top, the part that carried 3 men to another world, weighed barely 3% of that. 97% of the rocket existed for one reason: to lift the fuel needed to lift itself. And that entire structure only had to reach the moon, a target about 385,000 kilometers. The nearest star sits roughly 1 billion times farther than that. This is why Voyager isn't accelerating toward anything. It got its speed from swinging past Jupiter and Saturn back in the 1970s, stealing a sliver of momentum from 2 planets, then coasting ever since. No burn, no push, just borrowed velocity, slowly bleeding away to the sun's pull. We didn't outrun the problem. We just found one clever way around it. Once, using planets that happened to be lined up correctly. So if fuel is the wall, what happens when we bring in something more powerful? In 2018, a spacecraft called the Parker Solar Probe launched toward the Sun, not away from it, and began looping closer with every pass. Each loop, the Sun's gravity yanked it faster. Eventually, it hit about 690,000 kilometers per hour, the fastest anything built by human hands has ever moved. Now turn that ship around. Point it outward, away from the sun, toward open space. The speed disappears with it. That record only exists because the probe is falling toward a star. Cut the star out of the equation, and there's nothing to fall toward. Nothing pulling it forward, nothing free. Send that same record-breaking speed outward instead. Sustained. No more gravity assists, and reaching even the nearest star system still takes somewhere around 6,000 to 7,000 years. Not the edge of our solar system. The next star over. Every upgrade we've tried moves the ceiling a little higher. None of them removes it. And there's a second problem waiting on the far side of that ceiling, one that has nothing to do with speed at all. Every command NASA sends to Voyager, one takes nearly a full day just to arrive. Not because the technology is slow, because the signal, moving at the literal speed of light, still needs about 23 hours to cross the gap between Earth and a spacecraft that's barely started leaving. Send a command today, and confirmation it worked doesn't land back on Earth until sometime tomorrow. One question, and its answer, already cost engineers the better part of 2 days. And that's with the nearest, best-tracked spacecraft we've ever flown. Now imagine a mission that actually made it past the heliosphere, sailing years or centuries beyond where Voyager sits today. Push a signal 1 light year out, and the reply takes 2 years, round trip. 10 light years out, 20 years. There's no clever fix waiting to solve that. Light is already the fastest messenger the universe allows, and even light can't outrun distance at this scale. Every mission NASA has ever flown, from the moon landings to the Mars rovers, depended on a ground team close enough to react within hours, sometimes minutes. Send help, correct a course, talk a crew through an emergency in real time. That safety net disappears the farther out a mission goes. Past a certain distance, whatever leaves Earth is completely on its own, making every decision without anyone back home able to weigh in, or even learn something went wrong until the message finally arrives, long after it stopped mattering. We haven't built anything that's traveled far enough for this to bite yet, but it's waiting exactly where the fuel problem and the radiation problem both lead, further out in the direction where the silence outlasts any mission that could survive it. And silence isn't the only thing waiting out there. The moment a spacecraft drifts beyond the heliosphere, something invisible changes. The sun stops protecting it. Particles that have been crossing the galaxy for millions of years, flung out by exploding stars in systems we'll never see, begin passing straight through the hull. Inside the bubble, the solar wind blocks roughly 75% of that radiation before it ever reaches us. It's a shield we don't think about, because we've never lived without it. Step past that boundary and the shielding is gone. For instruments, that means slow, silent failure. For a human body, it means steady, accumulating damage, cell mutation, elevated cancer risk, long-term harm to the nervous system, adding up year after year with no way to undo it. We didn't just lose daylight out there, we lost the one thing keeping deep space from getting inside us. Now stack everything so far: the distance, the fuel, the radiation. Each one alone is survivable, in theory. Together, they don't add. They multiply against each other every single time. Put two numbers side by side and the picture stops feeling abstract. Clearing our own solar system with the best hardware we've ever built, roughly 30,000 years. Reaching Proxima Centauri after that, the nearest star beyond our own, a distance of 40 trillion kilometers, at Voyager's current speed. Another 73,000 years. Combine them, and a single, real mission using real existing engineering takes longer than the entire existence of our species just to reach the closest star in the sky. Not a galaxy far away, not the far side of the Milky Way, our next-door neighbor. Picture spending 50 years walking toward an exit, only to realize the corridor stretches on longer than the whole of recorded human history. That's what trapped actually looks like. No wall, no border checkpoint, just a slow, compounding math problem. Speed demands fuel, fuel demands mass, mass demands more fuel, and every extra year in transit demands a body that can survive radiation with no shield strong enough to carry. Fix one part of that equation, and another part gets worse. There is no version of it, using anything we currently know how to build, where the numbers stop working against us. So here's what actually answers the question, and it isn't the one the title seems to promise. We're not trapped because something is stopping us. We're trapped because leaving costs more time, fuel, and biology than anything we've ever built can provide, and every attempt to fix one part of that cost makes another part worse. The Oort cloud isn't a distant milestone we're steadily approaching. At our current pace, it's a finish line our species, in its current form, may never actually reach. Voyager 1, the farthest we have ever gone, the proudest achievement of 70 years in space, is still, right now, closer to the sun than it is to freedom. And maybe that's the part worth sitting with. Whatever civilization eventually does cross that line for real might not be remembered for reaching another star. It might simply be remembered as the first one that finally figured out how to leave home. Until then, every mission we launch, every record we break, every farthest ever headline we celebrate is still just movement within the same small neighborhood we've never actually left.